Good morning, students. I'm Professor Dhruvam Gaikwad, GA from GIDC Degree Engineering College. Uh, I would like to tell about these online sessions due to COVID-19. I hope you all are doing well, uh, referring the lecture notes and online uploaded material in Google Classroom. In addition that, I'm going to cover this chapter 3, last topic, the design of field coils in the subject design of DC machine and transformers. So up to now we have seen the armature design. Now the last portion is the field design. So in that case, I would like to give some introduction about the basic equations which will be helpful to solve the numericals. And then after we will try to solve the numericals. So any numericals, the MMF for the field winding is always required. It may be given or we need to find it. So for that there are the basic equations called ATF and IF into TF. So for that MMF for the field winding is equal to, is notation is ATF, F for field winding. It is unit is in ampere. Its equation is IF into TF. Or in another case, it is also known as MMF for pole. Why? Because field winding is mounted on the pole. That's why it is also called as MMF for pole. In examples, if we have not given the MMF for field winding, we can consider it as MMF for pole. And IF is the exciting current, or in some case it is known as the field current. And TF is the number of turns in each field coil. Okay. The next is length of coil. Generally, we need to find the length of the coil. So in that case, we need to consider the length of the mean turn. It is notation is LMT. So basically, there are the two equations for finding out the length of mean turn. One is 2 bracket LP plus BP bracket over plus 2 DF. This is the one equation in which LP is the length of the pole core, BP is width of the pole core, DF is radial depth of field coil. Okay, it is given in terms of the pole. In another way, sometimes we have given the outer diameter, outer turn and inner turn. So in that case, we can use the equation LMT is equal to LO plus LI by 2, and LO and LI is nothing but the length of outer turn and length of inner turn. So next basic part is resistance of each field coil. So how we can define it? We know the basic formula, R is equal to rho L by A. So same formula we can use over here. So Rf is equal to Tf into rho LMT by AF. So what is this TF? TF is nothing but the turns, number of turns of the field coil, because there is not a single turn, there are lots of turns over there, so we need to consider the turns. So we need to add TF in the calculation of RF. All the other remaining things are same, only the change is length. We have to take the length of mean turn. In another way, we can also find RF by Ohm's law. V is equal to IR. Instead of that, here EF and IF. EF is nothing but the voltage across the each field coil, which may be given to us, or we can easily find out. Suppose if we don't know the value of RF and we need to find the area AF, that means area of each field coil, then what we can do, write down the same equation. RF is equal to TF rho LMT RF rho LMT by AF. Now make the subject AF, put all other things as it is. Now try to put the equation from Ohm's law. Okay, So rho LMT by RF. So instead of that, we can get TF rho LMT divided by EF divided by IF. So what we can finally get? We can get in numerator IF, TF, rho LMT and denominator only EF. Now what is this IF into TF? Again go to the first step. This IF into TF is nothing but the MMF required for the field winding. So we can put it instead of IF, TF, ATF. So our final equation will be like this. So we can easily get the area if we don't know the resistance. Okay. Now the last point is the turns of field winding. Now this turns is number of turns depend upon the lots of parameters. First one is the space factor, height of the field coil HF, DF depth of the field coil and EF is the area of the field coil. So here it is the I need to correct this, it is HF and again it is DF and last it is AF. And the space factor is also need to be considered. It is based on the ratio of bare conductor and insulator. So it is sometimes it is given as 0.75 d by d1 whole square. So what is d and d1? D is nothing but the diameter of the bare conductor and d1 is the diameter of insulated conductor. Generally the insulated conductors d1 is greater than d always, because bare conductor is the conductor, you can say only the copper area, okay, and without insulation area. So only the current carrying part is called as the bare conductor and D1 is the insulated conductor, means there is a layer of insulation above this bare conductor. So D1 is greater than D. So now again, suppose we have given the loss, I square R loss in each field coil. It is denoted as QF and sometimes this QF can be considered as the power loss. So we can use it as a equation of the power also, as we are using it in a I square R formula in the resistive circuit. Similarly, we can use it over here. So sometimes loss is given. So we need to consider it as a power loss. And if we can found from that IF is equal to QF upon EF. So this formula also can be used to find out the field current. Again, the cooling surface of the each coil, there is the surface area which can be given by S is equal to 2 LMT in bracket AF plus DF. If we need to find, if we can find surface area, then we can also find the temperature rise. Temperature rise of coil theta M is given by QF into C divided by S. C is the cooling coefficient. QF is again we are taking as a I square R loss over the surface S and C is the cooling coefficient. C value of C is given to us. Okay, so actually the designer, what the designer can do, the main thing we need to keep in mind that the MMF required for the shunt field winding must be satisfy the conditions, means ATF ATF is MMF provided on the shunt field winding. It should be matched with the value of IF into TF, means we are calculating it IF into TF. So what we can do in that case, suppose our ATF is less than IF into TF, it is IF into TF is the multiplication, so keep in mind that. So if ATF is less than the product of IF into TF, what we can do, we can increase the depth of the winding so that our ATF will be increased. Vice versa, if ATF is greater than IF into TF, the depth of the winding will need to be decreased. So let me summarize this. What we can just analyze from this, if our MMF required for the shunt field winding is less than the product of IF into TF, we need to increase the depth of the winding to increase the ATF, and vice versa, the ATF is greater than the product of IF into TF, so already our MMF is more, so we need to reduce that MMF. So for a reduction of this ATF, we need to reduce the depth of the winding also. Hope you will get these basic concepts. In next session, we will see the examples. So thank you very much.